Now, my dear children of class 11 science, we go to the next topic, and this is actually a law that we are going to define and to express. Okay, and in the last YouTube video, if you remember, we discussed one important topic that is called principle of continuity. Now, in this particular YouTube video, we focus on the law, and this law is called Stokes' law. What law? Stokes' law. Now, Stokes' law basically measure the force, the effective force exerted on a body. And this will we take a body as a spherical body which fall in a liquid. So when a spherical body fall on a liquid, then there is some force, okay, exerted by the liquid in which the body is in contact with, okay, and that is actually measured by the law known as Stokes' law. But from Stokes' law, even we measure the velocity of the body when it fall in a liquid, and this velocity is also called terminal velocity. What velocity? Terminal velocity. But before we come to the expression of terminal velocity, we first try to understand the statement of what? Stokes' law. And the statement of Stokes' law says that the viscous force, what force? A viscous force acting on the spherical body. What body? Especially we take what body? A spherical body whose radius is say r, and that body is suppose is falling in a or moving in a what? Moving with a terminal velocity, and that velocity is v through a perfectly homogeneous medium. Perfectly homogeneous medium means the medium consisting of only one material, like perfectly pure medium, no impurities, presence of impurity and on. And that medium can be a liquid, it can be a gas. That means Stokes' law can be applied to a fluid also. It can be applied for liquid, it can be applied for gas. Having coefficient of viscosity, and the coefficient of viscosity eta is given by F, which is the viscous force, and this viscous force equals to 6 pi eta Rb. 6 pi eta Rb. So this is the expression that measures the viscous force acting on the spherical body, okay, when it falls in a liquid having coefficient of viscosity, body having radius r, and it falls with a velocity, and that velocity called terminal velocity, and is given by F equals to 6 pi eta Rb. So this is the mathematical expression of Stokes' law. But children, as I said, this Stokes' law measure by what amount of force that is exerted on the spherical body when it falls on any of the liquid. Falls on what? Any of the liquid. But from this Stokes' law, we can even determine the what? Terminal velocity in which the body fall in a liquid. Where you can see eta is the coefficient viscosity, as I said already, and 6 pi is basically constant involved in the expression. This is basically what? Constant involved in the expression. And basically eta is also constant for a given liquid at a given temperature. At a given temperature, given pressure and given density. Because you have learned already in the last YouTube video, coefficient of viscosity depends upon temperature, it depends upon pressure, it depends upon what? Density also. So suppose there is a liquid having same density at constant temperature and constant pressure, the coefficient of viscosity also remain constant. So that F is equals to 6 pi eta Rb. So this is the expression that measures the viscous force, okay, that exerted by the liquid on that spherical body when that spherical body fall in a liquid. Now, in order to understand this Stokes' law, statement of Stokes' law, okay, let me take a vessel. Let me just take a vessel, okay, containing a liquid. Containing what? Liquid. So I am taking liquid as a fluid. Okay. Now what I do, I drop the spherical ball. So from this point, okay. So when a spherical ball drops, okay, from through a liquid, okay. So spherical ball means basically this is the shape of the spherical ball, and this spherical ball has a what? Radius also. It has a radius also. So when it dropped on a liquid, then it moves with the velocity, and I consider that velocity is the what? Velocity? Terminal velocity. Okay, but spherical ball even has a what? Radius, and that radius is what? R. But basically what we observe in this case is that when a spherical ball, this is spherical ball, okay, when a spherical what? Ball, or we can say a body, we can take a body or ball. So when a spherical body or ball falls through a fluid, and means like we are taking out a liquid, we are taking a liquid of certain coefficient viscosity, then the layer of the liquid in contact with the ball, so layer of the liquid in contact with the ball also moves with the velocity, same as the velocity of the spherical ball. So at every point of the spherical ball, it moves the velocity, but the layer in which the spherical ball in contact with it also moves with the same velocity as the velocity of spherical ball. But the fluid or the liquid which is at larger distance, suppose this is the fluid which is at larger distance from the ball, okay, usually remains at what? Rest. Usually remains at what? Rest. Thus, a relative motion is set up. There is a relative motion set up between the various part of the layer. Various part of the what? Layer of the what? Liquid. This relative velocity is opposed by the viscous force. So when there is a relative motion occurred by the various part of the various layer of the liquid, okay, then definitely what force will set up? The viscous force is set up by the liquid, okay, because viscous force comes into play only when there is a relative motion between the different layer of the liquid, okay. That's why this relative velocity is opposed by the viscous force. As the velocity of the body increases, so when it falls in a liquid, when the velocity of the liquid or the velocity of the body, increases, the opposing force also increases. That means more viscous force exerts on the body. Means when B increases, viscous force also increases. Because as for the mathematical relation of Stokes' law, force and velocity are directly proportional to each other. When the velocity of this spherical body increases, the viscous force acting on that body also increases. But a stage will be reached when the body falls on that liquid, when the upthrust of the fluid, there is upthrust exerted by the fluid also. Remember this. There is upthrust exerted by the fluid, and this upthrust exerted by the fluid, okay, and the viscous force balance the weight of the body. That means the weight of the body always act vertically downward. There is a upthrust exerted by the liquid, and there is a viscous force also exerted by the liquid. So two forces act on the body, by the liquid. One is the viscous force because of the relative motion, and there is a upthrust also exerted by the fluid on that spherical body. But these two, viscous force and the upthrust exerted by the fluid on this spherical body, is exactly balanced by the weight of the body. So under this case, what happened? The resultant force acting on this spherical body becomes zero, and the body moves with a constant velocity. So this is very important. Body moves with a what velocity? Constant velocity. Which means there is no acceleration occurred by the body, because body acceleration according to Newton's second law when there is a force exerted on the body. But the situation or the stage will reach when the body falls in a liquid or fluid in such a way so that the weight of the body is exactly balanced by the upthrust and the viscous force exerted on the spherical body. So under this case, this body falls with a constant velocity, and this constant velocity is only called what velocity? Terminal velocity. What velocity? Terminal velocity. So children, remember this. Terminal velocity is the constant velocity occurred by the spherical body when it falls on the liquid, when the viscous force and the what upthrust exerted by the fluid on the body is exactly balanced by the weight of the what body, because you know weight act vertically downward, okay, and the viscous force and the upthrust exert in the upward direction, so that these two forces and weight exactly balance with each other. So under this case, we can measure a constant velocity occurred by the body, and this velocity is also called terminal velocity. That's why one thing you have to keep in mind, that viscous force limits the speed of the body falling in a liquid. Viscous force limit the what? Speed of the body falling in a liquid. So with this observation, children, Stokes prepared a law, okay, so that viscous force acting on the liquid can also express in terms of this terminal velocity of the body, and that is given by F equals to 6 pi eta RB. But children, remember this part. This force, viscous force, is measured when the velocity occurred by the body is the what velocity? Terminal velocity. This is called terminal velocity of the body. And from this viscous force, expression viscous force, that is from Stokes' law, we can even measure the expression of what velocity? Terminal velocity. So children, I have just stated Stokes' law and explained how this viscous force measured acting on the body can be measured in terms of what? Terminal velocity. Now in the next YouTube video, you learn the expression of terminal velocity that we can derive for any spherical body.